Hey everyone, if you're trying to make a make anything machine, one of the most fundamental things that you have to learn how to do is to analyze a shape. So there's lots of different ways to look at shapes in Shapes 2. There's the built-in shape analyzer, if you will, and you can click on any shape maybe in the jobs menu and look at it like this, either in the layer view or the quad view. And there's a shape code for it up here which you can copy and paste, which is super useful. But this doesn't help you automate things. So if you want to automate things, you're going to have to figure out how to take shapes apart and look at the individual layers and look at the individual quadrants of those shapes, and then use those to create logic for gates and things like that to allow shapes to pass through or not pass through as the situation dictates. So what you're looking at right here is a way to take a shape apart into its component layers. Um, there's a couple tools that are used to do this, and those are found in the simulated machines menu once you've unlocked this. Now there's an awful lot of machines in here. You have simulated rotators, reverse rotators. You can read them yourself. The ones that I find most useful are the simulated unstacker and the shape analyzer. Those two tools are essential, and the rotators, for doing most things in automation in Shapes 2. So the first thing we're going to look at today is taking a full shape and then subdividing that into layers and then outputting that layered data onto a transmission channel so you can use it somewhere else. So the first thing is, what shape are we looking at? Well, if you haven't really played around a whole lot, um, there's these things called signal producers, okay? And those signal producers they start out just plain like a null. But what you can do is configure them to have a shape code. Or they could have null, conflict, a number, or a fluid color, or an item code. Today we're going to be using mostly item codes. So where do you get item codes from? Well, you can create your own, but you can also get them from shapes that exist in the game itself. Like, you should be able to click on most shapes and there'll be an item code there. And what you could do is just copy that shape code, and then you can click on configure for your signal generator and then paste it in. So once you do that, then that is going to generate that shape code along a wire. Now, it's not obvious, but these wires don't just contain zeros and ones. They can also contain colors, they can contain nulls, conflicts, or entire shapes. And so it's that shape functionality that we're going to be using today. So I don't really need this one over here. I've put a couple representative shapes into some signal producers over here, and they've got a little toggle switch with them. This is a quick way, by the way, of um, choosing between different shape information if you want to play around with some test platforms and things like that. So making a little toggle button that'll turn on a transmitter, or a transistor rather, and letting that shape information flow through these wires. If you don't have a transistor here, then you get conflicts if you try to open one back and forth. They fight with each other. So these transistors are like diodes, kind of one-way deals. Anyway, like, you turn this one off, and then you could turn this one on, and then the wire would contain that shape data. You can see I've used a display here. All right, so this is a pretty basic way. Now, I've also stuck a global random operator shape receiver here. So let me turn this guy off, and you can turn this one on, and now it's putting out the shape that's in the random operator thing. So you can click this and then choose between 0 and 1 if you didn't know that. That's pretty essential later on if you're trying to run through the operator levels. So now that we know how to activate a wire or whatever we're trying to do with a shape, the next thing to do is figure out, well, what is this shape comprised of? Okay, in this case, we can look at the display right here and see that it's basically got, it's a two-layer shape with some shapes on the bottom and some shapes on the second layer. Pretty standard stuff. I've got a couple other things here for later that we can look at. So The next order of business is trying to separate that into layers. All right. And so don't get intimidated by this stuff. I'm going to go through it real quick, and it looks messier than it actually is. This next tool that we're going to look at is the simulated unstacker. And reading the tooltip here, it says simulate separating the top layer of a shape and does not break crystals. Great. So it simulates separating the top layer of a shape, which by itself is great, but you don't necessarily automatically know how many layers a shape has. And so if it's got 4 shapes, that would be layer 4. If it's got 3, layer 3, etc. And so what I would like, and what makes it easier for me, is to formally assign the shapes to bottom, bottom plus 1, bottom plus 2, bottom plus 3, etc. Really just bottom plus 3. That would give you the top layer. And that way I know which layers I'm working with. And so that just makes it easier to construct your make anything machines. You can use a top-down model, or you can use a bottom-up model. I tend to find that the bottom-up models work better, especially for crystals, than top-down. But I'm getting ahead of myself a little bit. So this business over here, once we have a shape that's being input into these wires and that's being carried around, it's carried to these basically 4 different little logic circuits here, if you want to call them that. Now, before I even talk about what these circuits are doing, understand that this is a circuit right here designed to have lots of displays so you can actually see what's going on from as the chain goes down. This is the circuit boiled down without any extra frills. All right. And so these are basically equivalent here. And if it makes it easier for you to digest without the displays, then that's why I've got them shown. But they both do the same thing. So what's actually happening with these things? This is the bottom layer right here. And we'll go here first because I'm trying to find out where the bottom is. All right, how many layers does this shape even have? So this makes heavy use of the XOR gate, which again is found in your logic gates. There's ANDs, there's ORs, NOTs, XORs, comparisons, and then transistors. This is the XOR gate. So what an XOR gate does is it activates if exactly one input is on. Now what does on mean? Well, on means anything but null. All right, so you could have colors, you could have shapes, you could have a number on one side of the gate, and if you've got a null on the other side of the gate, then it's going to output true, and then anything out that true is going to be on. So what I've got here is a series of comparisons. And so for your shape, this is going to, again, separate the top layer. And you can see what it's done here. So with the way this thing works, the top layer gets kicked out on the side, and then whatever's left over goes out the bottom. So you can see, because I put these displays here, that what gets kicked out on the side is the top layer of this shape, because that's what's being inputted. And then the bottom gets kicked out whatever's left. So it slices off the top, and then kicks out the bottom. Now, because there is something on both sides of this guy that come around to this XOR, then this transistor is not activated. You can tell because it's not glowing. Transistors that are activated are glowing. That means that the input to the top of them is true. All right. As opposed to, basically a 0 or 1. And most of the logic gates put out either a 0 or 1 as their output. So this particular XOR gate is putting out 0 or false because it's got something coming into both sides. So that shape continues to travel on down, and it goes into another comparison, and it gets sliced again. And so in this particular case, the top level is that which is left over from before, and then what gets kicked out of the bottom is null because there's nothing else below it. Now, because you've got a null on this side of this XOR, that makes this true. And so when that makes this true, it's going to output whatever's coming into the back end of it. And the back end of it happens to be this guy right here. So what this is basically saying is that there isn't anything else underneath this. All right. And so once you've got to the bottom, then it's going to kick out whatever was there before, and that activates this whole circuit, and you see that this transmitter now is going to put out the bottom level. All right, so um, the reason why these transistors are gang together like this, don't be misled, because you can disconnect all these and nothing happens, because this is the only one that's turned on right now. I'll put these back just for the sake of clarity. So even though these are all glowing, it's only glowing because this guy is true right here, and so that's the signal that's going out. All right. So now we found the bottom and we've made that the base. All right. And so this transmitter is now going to output this data, if you will, on its own little transmitter. It's blasting out this shape to the universe, essentially. Okay. So this logic does exactly the same thing, just without the display. So it maybe looks a little cleaner. And you can essentially see that the first, the first XOR gate that is outputting a true signal, which is this one, is going to output the signal that came in from that, all right, or the shape information that came in for that, and then output that. All right, so if it's not clear yet, it's going to get even more muddy or clearer depending on your disposition as we move on. So moving up a channel. So the input is the same. Now we're going to once again check the first, slice the first layer off. And the thing is now is that we've already figured out what the bottom level is. So now what we're going to do is come down here, and the first XOR that is true is going to activate the layer above that to give you the second layer. All right, now let me run that by you once more. The first on this one, the first XOR gate was going to give you the information that was on that level. The next one is the first XOR, because this is the bottom, once again, is going to give you the next level up, which was the previous one that we looked at before. Now it's a little complicated, but that's how it works. And so because this is the bottom right here, it's going to output the one above that for the next level up. All right, I said that a couple different times. Maybe it's clearer over here, is that the output of each one of these XOR gates is referencing the shape data from one level above it and making that active. Continuing that logic above, now we're going to go down 3 levels, find the bottom, and that's going to output 2 levels above it. Now there's nothing else on here, so these are going to be null. But if we change over to a different shape real quick, toggle that off, toggle this one on, it's got 4. All right. Now we can see that the base is outputting the bottom level. All right. Base plus 1, the bottom level is still true, but it's outputting the shape information from the layer above it. Moving up, the bottom is still true, but now it's outputting a shape that's 2 levels above it. And then lastly, the bottom is true, and that's outputting the shape from the one above it. And so by that means we managed to capture all 4 layers of this shape over here. And it doesn't matter how many layers that we have, it's always going to capture the bottom on this base level and the ones up from there. And so by this means we kind of bypass the fact that this is only pulling off the top layer, which is annoying. If it pulled off the bottom layer, we wouldn't have to do any of this stuff. We could just slice it 1, 2, 3, 4 times and it would be over. So this is kind of a workaround just because of the way this works. I prefer to have a dedicated channel for each layer starting at the bottom rather than starting at the top, and this is a way that I figured out to do it. Again, this logic looks a little messy because there's so many displays here, but you know, when I was putting this stuff together, I had to keep track of it myself, and so that was the easiest way to do it. But then after a while, I was like, well, can I make that more compact and a little bit more streamlined? And so if you do a little studying, I've got this blueprint. I'll add it to the bottom of this video. You can have it. So Once you have the layer data, the next most important thing to be able to do to help you on your way to make anything machine is subdivide a level into its individual quadrants. All right, so that you can study the individual quadrants on a particular layer. So I've outputted each one of these layers to a channel. In this case, I just picked 80. You can now pick any layer that you want or any channel that you want and put a number in there, and that'll just be your radio frequency if you want to call it that. TACAN channel maybe if you're a pilot. Anyway, we'll once you do that, I'll slide to the right a little bit, and I made this other platform where now I'm receiving these different channels. Now you can see that I've displayed each one of the individual layers that was outputted on these different channels from over here. And these can be anywhere on the map. That's the whole point of using these little transmitters. And so now we'll use the next most useful simulated machine, and that's the rotator and the shape analyzer. All right. So the shape analyzer is essential for this kind of stuff. And so what it does is it outputs the shape, type, and color of the northeast first layer quarter. Okay. Well, once again, first layer, does that mean the top or does that mean the bottom? Well, in this case, it doesn't matter because I've already separated it into individual layers. So I really feel like it means the first layer. Wow. I can't remember if it means the bottom or the top, but it doesn't matter because I always take them apart first. So at any rate, if you're looking at this guy, the input, well, the way this goes, the input comes in from over here, and what gets passed through is the northeast quadrant, and what gets kicked out the side is the color information. All right, and you can kind of see that if you study it. They updated the graphics before, you just had to kind of remember it, and I always forgot it. So once you have a layer data, or you can use it on a regular hole shape if you want, if you just have to remember whether it's the bottom or top, but this is the way I do it. Anyway, this information is cruising over this way, and what I've done here is I put 4 different displays in the order of the shape. So northeast, northwest, southwest, southeast. And so that was a poor choice because this particular one only has 3 shapes. Let me use one from over here. Just give me 1 second here. We'll kind of do a little rerouting. All right. All right. So now this is going to be looking at this shape right here. All right. And so what we've done here is the northeast is what this thing takes. And so I didn't have to do any pre-processing or anything there. I'm just taking that shape input, and what it's going to do, it's going to output the northeast shape type and the color. And so we've got the shape type is a circle and the color is blue. Now going over here, what I've done is I've done a rotator. And so it simulates rotating a shape clockwise. It's not actually rotating the shape, it's just rotating the image of that shape. Because again, these are all just shape information, if you will. They're not actual shapes that you're playing with. So what I've done here is I've rotated it 90 degrees, and then I've looked at it, and then I've rotated it back 90 degrees to put it back where it came from. And then I've outputted it here and the color value. All right, so if I did that twice and then put it back where it came from, then I get over here, and then the same thing here 3 times, and it's back. Now, for the purposes of a make anything machine, I find that if you're working with quads especially, just work with them in the northeast quadrant. Don't bother rotating them back to a place and try to just leave everything in the northeast and sort it out at the end. It just makes it a lot easier and your logic doesn't get all cluttered up. So this is all kind of an exploded view, but what it really boils down to is something like this. And so in a lot of my make anything machines, you'll see little modules that have 1, 2, or 3 rotators with an analyzer, and that's just in an effort to take a look at the different shapes. And so if you look at this one, you can kind of see that they're all in the northeast quadrant because I rotate the image of it and then examine it, and that's where it is. So this, yeah, anyway. Now, you can see that the color information is blocked here. If you actually wanted to use that, you'd have to separate these out a little bit for obvious reasons. But this is a way to look at what each individual quadrant of each individual layer is doing. Now, once you get that information, what is it that you do with it? Well, if you want to analyze it further, like out here, what I've kind of done is taken one of these quadrants here, the northeast quadrant, and I've put a couple little comparisons on there. And so this is how you kind of compare what is it you're looking for. In this case, I've made a pin. It might be a little hard to see in the video, but that's a pin. And this is a null, and this is a crystal. So how did I make these little the signal producers? Well, like I said before, you can just fix the save on me, so I'll just wait until it finishes with that. My game field's pretty full, so my save games are taking a while to actually do their thing. So here's a signal producer, and you can configure these any way you want. You can type your own shape in. This is how you get a single pin in the northeast quadrant. It's pin minus, and then minus, 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 minus. And that gives you a pin. Null is just null, and it's usually just spell out null. All right, and then a crystal is formed the same way, and that's crystal uncolored, minus, 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 minus. That's how you indicate blank quads, and it needs a full layer of information to display properly. So you have to have 4 placeholders, and a placeholder for no shape is just 2 dashes. And so when you're comparing with this guy, the only thing you need is something in the northeast quadrant, because it's not looking at anything else, and it actually is, and your equal won't be right unless there's nothing but the northeast quadrant. So make sure that if you're using the shape type function here, that you're only comparing that to a northeast quad. Otherwise, it will never be equal. Speaking of equals, you can change this to other stuff. Now I find equal and not equal to be the most useful. Um, there may be some benefit to, I don't know. I don't know why you'd use any of the other ones. I'm not that sophisticated. But what I've done here is just said that essentially if this is, um, you know, equal to, well, why is that? That's not true. Okay, that's why. Because I put a little not guy there. So when you say equal, it's either going to come out with a 0 or a 1 if it's true. For instance, if I put in another little guy here, let me copy that. Oops, I hate it when it does that. I had something else selected. Let me copy that little guy. I'll put one more here. And I'll make this, so that's a circle uncolored. Whoops, my caps lock must be on. Circle uncolored. Nothing, nothing, nothing. All right, and you can see now that that's true because that's comparing that to what's actually there, and this is highlighted. Now, once that's, you can see that if it's true, it's a number 1, and if it's not true, then it's a number 0. Good old binary stuff. What I did here, just for giggles, was to put a transistor with a color input on it, which is done like this. You say color and then minus whatever the color is. There's a list of colors in the game that you can see what the letters or the abbreviations are for them. And I made that the input to this little transistor. So what this is saying, there's a little not guy here. So this is false, but because I put a not there, it changes it to true, activates this guy, and makes this green. So I don't know what the utility of that is. It's just kind of cool. It's like, hey, it's green. So anyway, I just wanted to illustrate what you can, the fundamentals of logic and how you use that moving forward. If you decide to make your make anything machine, what you're going to find yourself doing is choosing, analyzing a shape, analyzing a quadrant of the particular layers of that shape, and then activating gates to either allow shapes to pass or prevent them from passing, as you use sorters and things of that nature. If you've looked at any of my Make Anything machines up to this point, then you might have seen stuff like that. But if you prefer to work on it on your own, maybe this is going to get you started on the right direction. It's kind of fundamental to the game, and there's nothing in the game that really helps you along with this. It's just kind of you work through it. But if this helps you get a head start on uh, performing logic operations and actually analyzing a shape, then it can really unlock the rest of the game's potential, which I think this is just part of the really cool aspect of this game altogether. And yeah, and then if you enjoy that, you can start working on making crazy stuff like this with big weird logic boards that do funny stuff. And anyway, you've probably seen some of my other videos, so, or probably not, because nobody watches my videos. But if you stuck around this long, I appreciate it. Like and subscribe if you can. It doesn't cost you anything. And I'll keep chucking out stuff if people find them useful. So thanks for sticking around. See you later.